I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to derive an expression for the fringe width. If we look at the module 4, we have already discussed the Huygens principle, the superposition of waves, and in our previous lecture we have seen the Young's double slit experiment. And with the help of this experiment, today we are going to derive the expression for fringe width. So let us see how we are going to discuss this topic. This is a brief outline of how we are going to go about the topic. Since we are deriving the expression for fringe width, let us first understand what is a fringe. So we'll see the basic definition of fringe first, and then we will understand how these fringes are formed. So the formation of the fringes, then the experimental setup, that is the Young's double slit experiment we need, and do the qualitative treatment. Understand the conditions for constructive interference and destructive interference, and then finally with these we are going to derive the expression for fringe width. And then we are also going to do the analytical treatment for intensity. We are going to determine the intensity of the wave that is formed at that particular position. Now let us understand the fringes first. Waves have an interference phenomena that gives rise to interference fringes. So we have already seen about interference. What is happening in interference? In regions where two light waves overlap, the waves' electric field vectors will add up, and if the light waves having the same polarization occur, they can either interfere constructively or destructively. And waves with constructive interference are always in phase, they have the same phase, and those who are interfering destructively, they are out of phase. They are out of phase. So this is what we have already discussed. The waves, when you have, they exhibit interference phenomena, and because of the interference phenomena we get the fringes, which we call them as interference fringes. How are we getting interference fringes? Is due to the electric field vectors getting added up. So when they are adding up, how we are seeing them as two waves? Either if they are in phase we have constructive interference, if they are out of phase we have destructive interference. Now to ensure that two interfering waves have the same polarization, what we are doing is we split a wave into two with the method called division of wavefront. So what we are doing, we are ensuring that they are having the same polarization, means they are in phase. So we are using the method of division of wavefront, means the same wave is passed through two closely spaced slits. The original source may not be coherent. We are just taking a monochromatic source. Light from the monochromatic source is made to pass through two slits which are placed equidistant from the original source. So by doing that, what we are getting a wave which is having the waves which are having the same polarization. Now the waves coming from these slits will interfere constructively or destructively. Now if light falls on the screen behind the obstacle, a pattern of dark and bright fringes appear on the screen. So that is what we are calling as fringes. So the light that is coming out from the two slits, they are sending out secondary wavelets. So these secondary wavelets, when they superimpose on each other, depending upon how they arrive at a point on the screen, if they are arriving in phase, we get a bright fringe. If they are arriving out of phase, we get a dark fringe. So on the screen, we have a pattern of dark and bright fringes. And this pattern, we are calling it as interference fringe pattern or simply an interference pattern. So these fringes, the bright band or the dark band, we are calling them as fringes. So the brighter lines are a sign of constructive interference and the dark lines are a sign of destructive interference. So this we have already discussed. Now the interference pattern's central fringe is caused by constructive interference. When we are talking about that the central fringe is a bright fringe, means the light coming from the two sources when they arrive at a point O on the screen, which is a central point, and they are traveling the same distance, though they travel the same path. So they are in phase. So when they are in phase, we have a central fringe which is very bright, and that is due to constructive interference. They are traveling the same distance to the screen, and so it is bright. And the central fringe, we are always calling it as the 0th order fringe. When we are naming the fringes, we will call it as M is equal to 0. That is the central bright fringe. Now, if you see the other waves, there are positions where the crest meets crest and also the trough meets trough. So when a crest meets crest or a trough meets trough, there is constructive interference because they are in phase. But when a crest falls on a trough, then we have the destructive interference. Now the dark fringes on the sides of the 0 order fringe are a result of destructive interference. So if the central fringe is a bright fringe, on either side of the central bright fringe, we have a dark fringe. So dark fringe on the upper side, we call it as M is equal to +1, and below it we call it as M is equal to -1. Now light from one of the slits travels half wavelength longer than the distance that the light travels from the other slit. So if light from the slit A travels a distance lambda, light from B travels a distance of half the wavelength extra. It is traveling more or half wavelength longer than the distance that the light from the other slit travels. So the first one we have taken as lambda. So from the second one, it is traveling lambda by 2 more. So lambda plus lambda by 2 gives us 3 lambda by 2. So at these locations where they reach traveling or having a path difference between them, then, and if the path difference is a half multiple of odd multiple of half the wavelength, then crest meets trough, and they gives rise to destructive interference, and we get a dark fringe there. So the first order fringes then follow the darker fringes. So what we have is a central bright fringe. Then on either side of the central bright fringe, we have the dark fringes. Then above the dark fringe, you again have a bright fringe. So you have a series of dark and bright fringes. Now the alternate bright and dark bands which are obtained on the screen is known as the fringe pattern. So what we are saying, we have a screen. On the screen, the central one is a bright band, which we are calling as a central bright fringe. So on the central bright fringe, after that above, we have a dark fringe. Below also we have a dark fringe. And then we have a bright fringe. Again a bright fringe. A dark fringe. Again a bright fringe. So what we are seeing here, these fringes which are formed, we are calling it as the fringe pattern, and these alternate dark and bright bands, we are calling them as fringes. Fringes are nothing but these bands that are formed on the screen due to constructive interference or destructive interference. Now if you see the graphical representation of the fringe pattern, so the central bright band you have here is the central bright band. This is the central bright band which we are seeing here. After the central bright band, we have a dark band. This is the dark band. And again here, this is also dark band. So if the path difference is lambda by 2 or a phase difference of pi, you have a dark band. And for a bright band, they are always in phase. So the central band is bright, the path difference is 0, and there is no phase difference also. So this is how you have a pattern. So what we are calling this as interference fringe pattern And these bands, we are calling them as fringes. So what you have, all these are bright fringes. We may call them as bands also, but we name them as fringes. So they are bright fringes. And all these are giving rise to dark fringes. So I hope this point of what a fringe, the definition of fringe is very clear. So the bands that are formed due to constructive and destructive interference, we are calling them as fringes. Now let us try to derive the expression. Determination of the distance of the bright and dark fringe from the central spot on the screen. Light from a narrow slit S illuminated by a monochromatic source is allowed to fall on two narrow slits A and B. So this is the monochromatic source S. Light from this source S now falls on two slits A and B. And these two slits are placed very close to each other. The width of these slits A and B is 0.03 mm and they are separated by a distance of 0.3 millimeter. Means the distance between these two is small d. We always denote it by small d, that is equal to 0.3 millimeter. Now, since the waves from S reach A and B and they travel equidistant because they are placed equidistant from S, so they reach here in phase. So the waves from A and B are in phase. So we call them as coherent sources. Coherent means always in the same phase. According to Huygens principle, the wavelets from A and B spread out and overlapping takes place. What does Huygens principle tell us? Each source acts as a source for secondary wavelets. So now secondary wavelets are coming out from A and B, and the waves that are coming from A and the waves that are coming from B will now overlap with each other. And when they overlap and a screen XY is placed at a distance of 1 meter from the slits, you will see equally spaced alternate bright and dark fringes, and we call them as interference fringes or bands. So we have already discussed what the fringes are. We may also call them as bands. And at a point O on the screen, waves from A and B travel equal distance and arrive in phase. So we have constructive interference and a bright fringe is observed. So the central fringe is always bright. Now let us see the geometry of this figure. This is one slit A, the second slit B. They are separated by a distance d. Small d is the distance by which they are separated. So let small d be the distance between the two coherent sources A and B. A and B are the two coherent sources sending out waves of wavelength lambda. Now XY is a screen placed parallel to AB. So AB is the plane of these two slits. Now we are placing a screen XY which is parallel to AB. And the distance between the source and the screen now is capital D. So XY is placed parallel to AB at a distance capital D. And C is the midpoint of AB. So of AB, this midpoint we are calling it as C. And O is the midpoint on the screen. O here is the midpoint on the screen. This is the midpoint on the screen. And this is equidistant from A and B. Means if you take the distance from A and also from B, it is equidistant. That is how we are taking the point O. Now P is a point at a distance x from O. We are considering a point P where waves from the two sources arrive, and this point P is at a distance x from O. Okay, this is what we are trying to see in this figure. Now, waves from A and B meet at P in phase or out of phase, depending upon the path difference between the two waves. So, the waves that are coming from A, the waves that are coming from B, both of them will interfere at P. They will superimpose on each other, and depending upon the path that is traveled by the two waves, they may be in phase or they may be out of phase. If there is no path difference, then they are in phase. If there is a difference in path, and if the path difference is an odd multiple of half the wavelength, then they are out of phase. So that is how we determine this point P. Now draw AM perpendicular to BP. So we are going to drop a perpendicular from the point A onto BP. So this is a perpendicular. So this is 90 degree. This is a right angle. We have dropped a perpendicular AM onto BP. And let us now calculate the path difference. Path difference here is the difference in the path traveled by the two waves. So what is the path traveled by the first wave? AP. What is the path traveled by the second wave? BP. So when we are talking about path difference, it is the difference in the path traveled by the two waves. So it is BP minus AP. BP by the from B, AP from A. These are the paths of the two waves. We are trying to find the path difference delta. Now, when we have dropped a perpendicular, so from the geometry of the figure, you can observe AP is equal to MP. AP is equal to MP. That is what we have written here. And now in place of AP, we are going to substitute MP. So delta is equal to BP minus AP, that is BP minus MP after substitution. So now what will be BP minus MP equal to? BP is this total length and this is MP. So BP minus MP will give us BM. This is BM. BP minus MP will give us BM. And BM is nothing but the path difference. Now what is the path difference delta between the two waves? That is given by BM. And now we'll write the formula for BM. Considering this right angle triangle ABM, this is the right angle and this is angle theta. So sine theta is equal to opposite side upon hypotenuse. So the opposite side is BM and the hypotenuse is AB. So sine theta is equal to BM upon AB. So what will BM be equal to now? BM is equal to AB sine theta. And AB is equal to small d. So we can write it as small d sine theta. And BM is nothing but delta, the path difference between the two waves. So delta is equal to d sine theta. So we have written BM is equal to d sine theta. And if theta is very small, theta is naturally small because these two slits are very close to each other. So this value of theta is very, very small. So when theta is small, sine theta is equal to theta. So we are going to substitute for sine theta, theta. So BM will be simply equal to d theta. BM is nothing but the path difference delta. So delta is equal to d theta. Now we'll consider the right angle triangle COP. What is the right angle triangle COP? COP. This is the right angle triangle. This is angle theta. Now consider tan theta. What is tan theta? Opposite side upon adjacent side. So what is the side opposite to this angle theta? It is OP. So we can write it as OP. What is the adjacent side? OC. What is OP equal to? The distance of the point P from the central bright fringe is taken as X. And the distance between the source and the screen is taken as capital D. So naturally CO is equal to capital D. So OP by CO is equal to X upon D. So tan theta is equal to theta. If theta is small, for small values, tan theta is equal to theta. So how do we write now here? Theta is equal to X upon D. Theta is equal to X upon D. So in the path difference formula, delta is equal to d theta, we are going to substitute for theta as X upon D. So delta, the path difference delta will be equal to small d into X upon D. This is what we got for theta. So we can write delta is equal to small d into X upon capital D. Now by the principle of interference, what we are having, the condition for constructive interference is the path difference is equal to n lambda. So this is the condition for constructive interference. What is the path difference we have got now? Small d into X upon capital D, that is equal to n lambda, where n can take the values 0, 1, 2 and so on. So if n is equal to 0, means there is no path difference, that represents the central bright fringe. And if n is equal to 1, then you have a path difference equal to lambda, 2 lambda, 3 lambda and so on. So now from this, we are going to write the formula for X. So we are taking this, we have substituted for theta X upon D. So small d into X upon D is equal to n lambda. So X will be equal to n lambda capital D upon small d. Now if n is equal to 1, you have X is equal to lambda D by D. Means the distance of the first bright fringe from the central fringe is X, that is lambda D by D. So X is equal to lambda D by D. So this gives the distance of the nth bright fringe from the point O. So if n is equal to 1, we get the distance of the first bright fringe. If n is equal to 2, we get the distance of the second bright fringe and so on. Now bright bands are formed as a result of constructive interference and they are the positions of maximum intensity. So we are going to write the condition for maximum intensity. What is the condition for maximum intensity? We have seen the path difference should be an integral multiple of lambda, and we have derived the expression for path difference X into small d upon capital D. So that should be equal to n lambda. So X will be equal to n lambda D by D. So this gives the position. Xn is what? The position of the nth bright fringe. And when n is equal to 0, we have the central bright fringe. So this is what we need to understand. The condition for constructive interference and then the position for the bright band. Now we are going to see for destructive interference. So what is the condition for destructive interference? The path difference should be an odd multiple of half the wavelength. Means path difference is 2n plus 1 into lambda by 2. If n is equal to 0, we get lambda by 2. N is equal to 1, we get 3 lambda by 2. N is equal to 2, 5 lambda by 2 and so on. So they are all odd multiples of half the wavelength. So we are going to write the expression for X. So X is equal to, that is the distance of the nth dark fringe from the central fringe. Central bright fringe is capital D by D into 2n plus 1 by 2 into lambda. We are just going to substitute the formula. So X is equal to capital D by D, because we know delta is equal to what we have seen, small d into x by capital D. So we are going to equate the two now. Because we have seen path difference is equal to 2n plus 1 into lambda by 2. So we are going to equate and write the formula for x. Capital D by D into 2n plus 1 by 2 into lambda. So suppose if n is equal to 0 here. So if n is equal to 0, what do we get? Capital D by D into lambda by 2. N is equal to 1 implies capital D by D into 3 lambda by 2. N is equal to 2 implies capital D by D into 5 lambda by 2. Means at all these positions we will get a dark fringe. So this equation gives the distance of the nth dark fringe from the point O. O is the central spot on the screen. So on the screen what we are going to have is alternate dark and bright bands on either side of the central band. Now these dark bands are formed due to destructive interference and they are the positions of minimum intensity. Dark means minimum intensity. Bright means maximum intensity. So what is the condition for destructive interference? The path difference should be an odd multiple of half the wavelength. So n plus half lambda, or x into d by d is n plus half lambda, or xn will be equal to n plus half into lambda d by d. Xn here is what? It is the position of the nth dark band from the central band. Now we are going to derive the expression for fringe width. So once we understood the phenomenon of interference, and in interference we have seen two, the constructive interference and the destructive interference. We have seen the fringe pattern, how it is formed because of this interference. So when there is constructive interference, we are getting the bright bands, and when there is destructive interference, we are getting the dark bands. And these bands, we are calling them as fringes. Now we are going to determine the bandwidth or the fringe width. Both mean the same. Bandwidth or fringe width. Now what is this fringe width? The distance between any two consecutive bright or dark bands is called the bandwidth. So how do we understand it? Now if you take the screen, there is a central bright band. This is the bright band. We have a dark band, bright band, and so on. Dark, bright. This is the central bright band, then we have bright. The distance between any two consecutive bright bands means this is the central bright band and this is the next bright band. What is the distance between the two? That gives us the bandwidth or the fringe width. So the distance between the n plus 1th and the nth order consecutive bright fringes from O is given by xn plus 1 minus xn. So xn plus 1 gives the distance of the n plus 1th fringe. Suppose I am taking n is equal to 1. So if n is equal to 1, this will be x2 minus x1. That means the distance between the first bright fringe and the second bright fringe. If I take n is equal to 2, so it will be x is equal to 3 and x is equal to 2. So that is what we are talking about here is the distance between any two consecutive bright fringes. 1 and 2, 2 and 3, or 3 and 4, and so on. So now let us write the formula for xn plus 1. So we have the formula for x as x is equal to capital D by small d into n lambda. This is for xn. Now what will be the formula for xn plus 1? In place of n, we are going to put n plus 1. That gives us the distance of the n plus 1th bright fringe. This is the distance of the nth bright fringe. This will be the distance of the n plus 1th bright fringe from the central fringe. So now what we are going to do, we are going to substitute. because we know the fringe width beta is given by xn plus 1 minus xn. So this is equal to capital D by D into n plus 1 lambda. This is xn plus 1 minus capital D by D into n lambda. This is for xn. Now let us expand these terms and find the value of xn. So xn will be now equal to, we get capital D by D into n lambda plus capital D by D into lambda minus capital D by D into n lambda. So capital D by D into n lambda, capital D by D into n lambda gets cancelled. So we have beta is equal to, this is what we are going to write it as, beta is equal to, what we are left with is only a single term, capital D by small d into lambda. So what is beta here? It is the distance between any two consecutive bright fringes, that is given by capital D by small d into lambda. Here you need to understand the terms here. Capital D is what? It is the distance between source and screen. Lambda is the wavelength of light we are using here, wavelength of the light that is passing through the two slit, wavelength of the light, and small d here is the distance between two sources. It is the distance between two slits. A and B we have taken two slits which are placed very close, that is small d. So now the fringe width depends upon capital D, the wavelength lambda, and also small d. Now similarly what we will do, we will try to do the distance between two consecutive dark bands, and we will also see that it is also equal to capital D by small d into lambda. Since the bright and dark fringes are of the same width, they are equispaced on either side of the central maximum. So we have seen on either side we are having alternate dark and bright fringes. We have already done for the bright fringe the distance between any two consecutive bright fringes. Now we are going to do for dark fringe. So for a dark fringe, what is the condition we have? Xn is equal to capital D by D into 2n plus 1 into lambda by 2. So this is the distance at which a dark fringe is formed. Okay. Now if we want to find the fringe width, that is the distance for between two dark fringes. So I will write the distance for the n plus 1th dark fringe. So what is the distance at which the n plus 1th dark fringe is formed? Capital D by D into 2n plus 1 plus 1 into lambda by 2. So the fringe width beta will be given by xn plus 1 minus xn. So this is what we need to understand. We have written the distance for the nth bright fringe. We have written the distance for the n plus 1th bright fringe. If we want to find the distance between these two, sorry, they are dark fringes. If we want to find the distance between the two dark fringes, so we are going to subtract xn plus 1 minus xn. That gives us the fringe width beta. So let us substitute and then simplify. We'll write it in the next slide. So xn plus 1 minus xn. So for xn plus 1 we are going to write this expression capital D by D into 2 n plus 1 plus lambda by 2 minus xn. What is xn? Capital D by D into 2n plus 1 lambda by 2. So let us expand these terms. So when we expand these terms, we have capital D by D into 2n into lambda by 2. So this gives us n lambda. Then here we have 2 plus 1, 3. So plus 3 lambda d by 2. And here what we have? Minus capital D by D into 2n lambda by 2. So capital D by D into n lambda minus, here if you are having this 1 lambda by 2. So D by D into lambda by 2. So plus dn lambda by d minus dn lambda by d will get cancelled. So what we are left with here is capital D. Here also we have small d in the denominator. So capital D by small d I have taken common. So what we have here is 3 lambda by 2 minus lambda by 2. So 3 lambda minus lambda, 2 lambda by 2. So this gives us d into lambda by is beta. So that is what we are writing here. B is equal to capital D by D into lambda. So when we have seen for bright fringe, also we got beta is equal to lambda D by D, where capital D is the distance between the source and the screen. Small d is the distance between the two slits and lambda is the wavelength. So what we understand from this is the distance between any two bright fringes or the distance between any two dark fringes is the same, lambda d by d. And this fringe width depends upon three parameters: capital D, wavelength lambda and small d. So now if the distance small d increases, then what happens? If the distance between the two slits increases, the fringe width will decrease. They will be very closely spaced. Means if small d increases, the fringe width beta decreases because they are inversely proportional. So as the distance between the slits increases, the width of the fringe decreases. And if capital D increases, means you are keeping the screen very far from the slits, then the fringe width will gain increase. And if lambda increases, the fringe width increases. So this is the dependence of the fringe width upon lambda, small d and capital D. Now we are going to look at the analytical treatment for intensity. We are going to derive an expression for intensity. So when they are arriving in phase, we are having a bright band, but what will be the intensity of the bright band? And when they are arriving out of phase, we have a dark band, and what will be the intensity of the dark band? So to do that, we are going to do an analytical treatment with the help of these equations. So let us represent the first one. First wave, the displacement of the first wave is denoted by y1 is equal to a1 sine omega t. This is the displacement of the first wave. Now we are going to take y2 is equal to a2 sine omega t plus delta, means they are differing by a path difference of delta. So this will be the displacement of second wave. Now when these two waves arrive at a point simultaneously, the resultant displacement at that point will be the vector sum of the two displacements. So the resultant displacement at that point, suppose these two waves are arriving at a point P. Now the resultant displacement at the point P is given by y, which will be the vector sum of the two displacements, that is y1 and y2. So let us substitute for y1 and y2 from these two equations. So what is y1? a1 sine omega t. And y2 is a2 sine omega 2 plus delta. So we have just done the substitution because the resultant displacement is the vector sum of the displacements due to the two waves. So y is equal to y1 plus y2. So now what we are getting, y is equal to a1 sine omega t plus a2 sine omega t plus delta. Now I am going to expand this term. We are writing a1 sine omega t as it is, and we are going to use the formula sine a plus b. is equal to sin A cos B plus cos A sin B. Simple trigonometric formula we are going to use. So for sin omega t plus delta, I am going to write sin omega t cos delta, that is sin A cos B, plus cos omega t sin delta, that is sin cos A sin B. Now expand. Sin omega t we have here. We can write this again as A1 sin omega t plus A2. I am just taking A2 inside. Otherwise, I am opening the bracket. You can understand. A2 sin omega t cos delta plus A2 cos omega t sin delta. So in this term, first term you have sin omega t, second term also you have sin omega t. We can take out sin omega t common from both the terms. So when we take out sin omega t from both these terms and write here, what is left in the first term is A1 and in the second one we have A2 cos delta. So we are going to write sin omega t into A1 plus A2 cos delta. Plus here we have cos omega t sin delta and we have A2. So A2 cos omega t sin delta, I have taken out cos omega t and written it as A2 sin delta. So let this be equation 1. We have taken sin omega t outside and we have A1 plus A2 cos delta. We have taken cos omega t outside, we have A2 sin delta. Now let us consider A1 plus A2 cos delta is R cos theta. We are doing a substitution. For A1 plus A2 cos delta as R cos theta and A2 sin delta as R sin theta. These two are very important. We are going to use them again. So this is a substitution. So substitute A1 plus A2 cos delta is equal to R cos theta and A2 sin delta is equal to R sin theta and put it in the equation 1. So what will be our equation y? Y will be equal to R sin omega t cos theta plus R cos omega t sin theta. So here in both the places I have R. So we are taking out R. So I can write it as R into sin omega t cos theta plus cos omega t sin theta. Again, this is of the form sin A cos B plus cos A sin B. So, which can simply be written as sin A plus B. So, what I am going to write here is R into sin. What is our A? Omega t. What is our B? Theta. So, the whole thing can be written as R sin omega t plus theta because we are identifying the formula. So, sin A cos B plus cos A sin B is sin A plus B. So, we are writing it as sin omega t plus theta. We have the amplitude as R. So, y is equal to R sin omega t plus theta. Now, we will consider equation 2 and 3. We will square them and add them. So, what is our equation 2? R cos theta. So, squaring you get R square cos square theta will be equal to A1 plus A2 cos delta whole square. That is squaring on both sides. Equation 2. Equation 3 also we will do the squaring. So, that gives us R square sin square theta is equal to A2 square sin square delta. Squaring equation 3. Now we have to, after squaring, we are going to add squaring and then adding. So when we add the left hand side, what we have, R square is common. We have sin square theta plus cos square theta. And here before adding, we are going to expand this term. This is like A plus B whole square. So A plus B whole square means we will write it as A1 square plus A2 square cos square delta plus 2A1 A2 cos delta plus A2 square sin square delta. So what we did here in the first step, we have just done the squaring and adding. Squaring and adding, we are having this. Now what we have done, we are going to expand this term. So sine square theta plus cos square theta is equal to 1. So what we have here is simply r square is equal to a1 square plus a2 square. For a2 square here you have cos square delta and then we have sine square delta. So we write cos square delta plus sine square delta plus 2a1 a2 cos delta. Again this becomes 1, sine square plus cos square is 1. So what we are left with is r square is equal to a1 square plus a2 square plus 2a1 a2 cos delta. Now what is intensity? Intensity is nothing but the square of the amplitude. Here r represents the amplitude or the resultant amplitude of the wave, of the resultant wave. So r square is nothing but I. So we can write the intensity I is equal to a1 square plus a2 square plus 2a1 a2 cos delta. So we have derived an expression for intensity from, because the amplitude, the square of the amplitude gives us the intensity of the wave. So I is equal to a1 square plus a2 square plus 2a1 a2 cos delta. Let us now put the conditions. So what is the condition for maximum intensity? So the condition for maximum intensity is cos delta should be equal to plus 1. So when will cos delta be equal to plus 1? So let us understand how cos delta will be plus 1. Suppose if the phase difference delta is equal to 2n pi, means if n is equal to 0, delta is equal to 0, means there is no path difference. If n is equal to 1, that means there is a difference of 2 pi. And for all these values, that is delta is equal to 0, 2 pi, 4 pi and so on, the path difference will be n lambda. So whenever there is a phase difference of 2 pi, there is a path difference of lambda. So for all this, the path difference is n lambda. So how do we write the intensity now? We will substitute for cos delta as plus 1. So when you write cos delta is equal to plus 1, I will be equal to a1 square plus a2 square plus 2a1 a2. That is what we are writing here. Putting cos delta is equal to plus 1. So this is of the form a plus b whole square, a square plus b square plus 2ab. So we are going to write it as a1 plus a2 whole square. Now if a1 is equal to a2 is equal to a1 is the amplitude of the first wave, a2 is the amplitude of the second wave. Suppose if you are taking the two waves, this is the first wave and this is the second wave. The amplitude of these two are the same. A1 is equal to A2 is equal to A. Then we are going to substitute here. I maximum will be A plus A whole square. A plus A is 2A, whole square will be 4A square. So what is the maximum intensity given by? 4A square. So I max is equal to 4A square. Wherever you have maximum intensity, it will be 4A square. Now what is the condition for minimum intensity? It is cos delta is minus 1. So what is the phase difference in case of minimum intensity or for the dark band? 2n plus 1 into pi. Means they are out of phase. So if you take n is equal to 0, so delta will be equal to pi. N is equal to 1, it will be 3 pi, 5 pi and so on. So the values of delta are pi, 3 pi, 5 pi and so on. So the path difference is 2n plus 1 into lambda by 2. So for all these values we have a path difference of 2, 1 plus 1 into lambda by 2. So what we are going to write for cos delta is minus 1. So if the value of cos delta is equal to minus 1, so this will be the path difference, this will be the phase difference, and we are going to write I minimum. I minimum will be a1 square plus a2 square minus, because cos delta is minus 1 into 2 a1 a2 we get minus 2 a1 a2. So this is of the form a minus b whole square. This will be a square minus 2ab plus b square. So we are going to write a1 minus a2 whole square. And if a1 is equal to a2, if they are of the same amplitude, the first wave y1 and the second wave y2, they have the same amplitude, then we put for a1 is equal to a, for a2 is equal to a minus a is 0. So the minimum intensity is 0. So this corresponds to dark bands. So the dark bands here are completely dark. The intensity is very minimum, that is 0. So let us see the formation, how they are formed. So formation of fringes is in accordance with the law of conservation of energy. So what is conservation of energy here? Energy is neither created nor destroyed. It can only be converted or it can only be distributed. So what we see here is intensity at maxima increases at the expense of minima. So wherever there is a minima, this energy is distributed in the maxima. So there is no destruction of energy due to interference. Only thing is, it is distributed accordingly in the form of a pattern, interference pattern, bright and dark, bright with maximum intensity and dark with minimum intensity. We have already calculated the expression for I maximum. The maximum intensity is given by 4a square and the minimum intensity is given by 0. So what do we see here? The central fringe at O is maxima. So this will be 4a square, and this is the first dark fringe at pi. They are exactly opposite in phase. So the dark fringe where it is 0. Again you have a bright fringe 4a square, then a dark fringe 0. So you see here these are all odd multiples wherever it is minimum, pi, 3 pi, 5 pi. And on the other side also minus pi, minus 3 pi, minus 5 pi. All these corresponds to minimum intensity or the dark band. And the regions, this is the central bright band for 0, then 2 pi, 4 pi, 6 pi and so on. We'll have the bright fringes. All these have the maximum intensity. So thank you. If you want any reference for this expressions, you can refer to Palaniswamy, Engineering Physics by Palaniswamy, and also Engineering Physics by Gaur and Gupta. Thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.